In this video, we'll be discussing about crystallographic planes and Miller indices. So let's begin. In the previous lecture, we discussed about the crystallographic directions of the Miller indices. We had this cubic unit cell in which we identified crystallographic directions. Now we'll be identifying the crystallographic planes, which will be given to us in the form of Miller indices. So Miller was basically a British scientist who was a crystallographer, and he helped in identifying the planes in a unit cell. So here are some rules that if the plane passes through the origin, select an equivalent plane or move the origin. Okay, it's the same as discussed in the directions video. So if you do not get this point, just look to the crystallographic directions video and then come to Miller indices for crystallographic planes video. So next we have that determine the intersection of the plane with the axis in terms of ABC. What does it mean to say that you have to identify the intercepts basically at which your plane is intersecting the Cartesian coordinate system of x, y, and z axis. Okay. So once you have the intercepts, then you have to take the reciprocal of that intercept. And if you know that if your intercept is 0, so if you will take the inverse of 0, so basically 1 upon 0 would be infinity. So we'll also be discussing then that how do we plot this infinity. Then we have to simplify it. We have to convert the smallest integral, which is an optional point, and enclose by parentheses, basically parentheses this curve brackets, which is used to identify the Miller indices for the crystallographic planes. Okay, so let's just start practicing it. Before that, let's see this Miller indices for planes. It says that HKL in the parentheses you represent the crystallographic plane, the x, y, and z coordinates. And if you are representing a family, so you will be representing it in a curve bracket as we represented the crystallographic directions in a triangular bracket. So here we are representing the family of crystallographic planes in a curve bracket. Okay. So we will also be discussing the families later on in the next slides. In the cubic system, planes having the same indices regardless of order or sign are equal. So if in a cubic system, if the planes are of the same family regardless if they have a negative sign or not, they would be equal. Also be discussing this point later on. And the family of planes contains all those planes that are crystallographically equivalent, that is, have the same atomic pattern. So if there's a family of planes, so the atomic packing of that plane would be equal in all the for all the indices. Alright. So basically this is the main point to remember while identifying a plane. That is, first of all, you have to find out your intercepts, which will be given to you, or you have to find it out. Then you have to take the reciprocal of the intercept, and then you have to simplify it so that you can easily plot it. And if you already have a Miller index given to you, so you take the reciprocal of it, and then by taking the reciprocal of it, you will be able to find the intercepts, and then you will be plotting the intercepts, and then you'll be identifying the plane in the unit cell. So let's begin the practice. Here you can see that there are certain planes 0, 0, 1, in which you can see that there is no such point in the x coordinate, in the x direction, and no in the y direction, but there is one in the z direction. Here is recorded here, and then these x and y are infinity, because we'll be taking the reciprocal of it. 0 upon uh, so 1 upon 0 is basically infinity, 1 upon 0 is also infinity, and 1 we have plotted over here. So we'll be plotting infinity over there. Then here we get 1, 0, 0, 1 plane. Similarly, there is 1, 0, 0 plane over here, 0, 1, 0 plane. Here, as these three are of the same family, you rotate this cube, you will get to that all these planes are basically same. Then we have 1, 0, 1, 1, 1, 0, and 0, 1, 1. Then we have 1, 1, 1, minus 1, 1, and 1, minus 1, 1. So we'll be practicing some of it, and some of it you have to practice by your own. So we'll be following these three rules, these three steps: basically intercept, reciprocal, and simplification, or the reverse of it. So here is a crystallographic plane given to us. So first of all, what we'll do is we'll identify the intercept of it. So if this is 1, this is 1, and this is 1, and if this is half, this is half as well, this is half as well. So what are the coordinates, what are the intercepts which we are given is 1 upon 2, 1 upon 2, and 1 upon 2. So first step is identifying the intercepts. Then we'll be taking the reciprocal of it, which will be 2, 2, and 2. And then we'll be simplifying it with the smallest number, that is 1, 1, 1. We'll be taking 2 as constant. 1, 1, 1 is the Miller index for this example. Okay. Next we have this point. You can see simply that this has intercept 1, this has intercept 1, intercept 1. Basically 1, 1, 1 are our intercepts. Then we'll be taking the reciprocal of this. That would again be 1, 1, 1. And if we simplify this, we'll again be getting 1, 1, and 1. So basically this is the Miller index of this. So you can see over here that this plane and this plane have the same Miller index. So why it does it? Why it is same? Because these both are parallel. So for parallel planes, you will be getting same Miller indices. All right. Either you represent it like this, either you represent it like this, or you represent it. You take it as 2, 2, and 2. It will all be same because all these would be parallel. Okay. Next, let's practice an intercept which is given to us, that was 1, 2, and 1. So this is basically the intercept. I'll mention as a marking I for the intercept. So let's plot the intercept. For x we have 1. We plotted somewhere here. For z we have 1, and for y we have this plotted somewhere over here. This is 2 for y. Okay. So this is 1, this is y is 2, and this is y is 2 and x is 1. Okay. So this is somewhat our intercept. So we'll be taking the reciprocal of it. The reciprocal of it would be 1. 1 upon 1 is 1. 1 upon 2 is 1 upon 2 half, and 1 upon 1 is again 1. So we'll be simplifying it. We'll be multiplying it by 2. We'll be getting 2, 1, and 2. So this would be our Miller index for this. But if we are given, for example, if we are given this Miller index and we have to plot it on the unit cell, so what we'll do, I just change the color first so that you can easily distinguish that. If you are given 2, 1, 2 as the Miller index, okay, and you have to plot it. So what you will do is, first of all, you will take the a reciprocal of this. So the reciprocal of this is 1 by 2, and for this it will be 1, and for this project to be 1 by 2 again. Okay, so let's plot it. For x this is 1 by 2, for z this is 1 by 2, and for y it is 1. Is there. We will be joining these all, and you can see that the orange plane and the red plane both are parallel. So since these both are parallel, uh, both of these planes are the same. Either you draw it like this or you draw it like this. It's basically the same. But it's better to draw inside a cubic cell, because you don't have another cube over here, and you don't have the exact dimensions, the exact intercepts over here. So it's better to just draw your plane inside the cube. Okay. So let's do another question. For example, you have 1, 2, 3, 4. So these are the major indices. So since I am making these parentheses, so it means that this is the major index, not the intercept. So we'll be converting this into the intercept form, and then we'll be plotting in our cube. So first of all, we'll be taking the reciprocal of this. That is 1 upon 1 is 1. This is 1 upon 2, and the z part is 1 upon 4. Okay, so let's plot it in the cube. For x we have 1, the intercept is 1. For y the intercept is half, 1 by 2, and for z it is 1 by 4. Somewhere over here. Okay, so this is not exact again, not very accurate. The triangle is not very accurate. You have to make an accurate triangle with the help of a ruler. So this is basically the intercept of the plane for 1, 2, and 4. Alright. Next, let's practice for 1, 0, and 1. Again, this is a major index because this is included inside the parentheses. So what we'll do is first we'll take the reciprocal of this again. So 1 upon 1 is 1. 1 upon 0 is infinity. Recording infinity. 1y, and 1 by 1 again is 1 for z. Let's erase this. Continue. So for x we'll be taking 1. For y we don't know, and for z we'll be talking. So in the y direction it will be going in this direction, that is infinity. So it could be going anywhere. So what we have these 2 points. We'll be joining these 2 points first, and then this is going, the plane is moving to the y direction in infinite intercept. So what we'll do, we just take a parallel line against this. Only on the rails, and again, it's not an accurate line I'm drawing, but draw an accurate straight line. Basically, this plane is the 101 plane, and this is the intercept. This is the intercept for this. Okay, so now let's see a question. It says draw 101 and 111 planes in a cubic unit cell and determine the major indices of direction which are common to both the. So what we'll do is first of all we'll plot these 2 major indices, and then we'll find the common direction between both of them. So I'll draw the first one with yellow and the other one with orange. So 101 I'll be drawing. So for 101 I'll take it as 1, infinite, and 1. So you see that x is 1, z is 1, and y is infinity. So this is the parallel there. One line over here, another over here. So this would be the 1, 0, 1 plane, and the other one is 1, 1, 1. So I will change the color of the pen. So 1, 1 is z, we have 1 in z, we have 1 at x, we have 1 at y. So we sign this line and okay. So let's mark the points first. The green, I'll be marking it as, this would be as A, B, C, D, and the other one is, yeah. So we have 5 points over here. So now what is the question says determine the Miller index of the direction which are common to both the planes. So the common direction is this one. As you can see that the red line and the yellow lines both are on top of each other. So this is the common direction, and it can be from B to A and can be from A to B. So you can see that these directions are parallel but are different, but they would be within the same family because the direction you can see is same but opposite. Okay. If we calculate the direction from A to B, that is this one. Yeah. So A and this direction from A to B would be, we are going you can see that A is the origin and we have moved the origin to Z, so Z would be negative. There is no Y over here, so Y would be 0, and there is 1 towards X, so this would be the direction of the common plane. If we are moving it downwards, if we are looking at it as downward, but if we look at just at this, it is B to A, such the direction would be -1, since we have moved the origin now to from 0 to X, so this would be a moving -1 in the X direction and 1 within the Z direction and 0 in the Y direction. So it would be -1, 0 and 1. So since these two are from the same family, you can only write one of them, which will also be correct. So this is how we determined the common direction to both the planes 111 and 101. Okay. Next we have in a cubic cell, find the angle between normal to the planes. So you can see that we have two planes, that is 111 and 121. So if we if 111 is this plane, let's suppose I change the color of the pen. If 111 is this plane and if 121 is this plane, so the direction of these planes would always be perpendicular to them. Okay, so the angle between this is what you have to find over here. So again, reading the question, in a cubic cell, find the angle between normal to the planes 111 and 121. So these are the two planes which I just set it, and this is plane 1 and this is plane 2, and the direction would always, the directions of these planes would always be perpendicular to them. Okay, so here would be an angle. This cannot be, this may be 90, but this may not be 90. So you will be using this formula to find out the angle, but this formula, as we discussed in the previous video of crystallographic directions, so this formula is for the directions. So to make it easy, I'll just say that if the direction is 1 1 1, if this plane has a direction 1 1 1, so the plane 1 1 1, so the direction of this plane would also be 1 1 1, which will be perpendicular to this. And for this plane which has the direction which is the plane 1 2 1, will have the direction which is perpendicular to this plane 1 2 1. It will have the same direction coordinates. Okay. So what we'll do is this is u1 u2 and u3, u1 v1 and w1, and this is u2 v2 and w2. So we'll be plotting this in the formula, and we can calculate the angle between these planes. So this is a very important question, and now you know how to find the angle between the planes, and you also know that the direction of the plane which has the same indices is always perpendicular to that plane. Okay, so you can now calculate this theta. Now here you can see that these are the family of planes. This is 1 0 0 1 0 1 0 0 0 1 minus 1 0 0 0 minus 1 0 and 0 0 minus 1. So these are the family of planes. You can see that if you rotate it along the axis, it would have you will see the same plane. So that is the reason why we convert them into a family. Again, this is another family of 1 0 1 1 1 0 0 1 1 1 0 minus 1 1 negative 1 0 0 1 and negative 1. So this is a family of 1 1 0 degree. Before moving forward, let's do some practice with the negative signs of indices. For example, if you are given an index as 2 1 and 2, so this is an index is given to you, that is in the brackets. So what you'll do, first of all, you'll be taking the reciprocal, that would be 1 by 2 1 and 1 by 2. Okay, so these would also be the intercepts which we'll be plotting, and if this is negative, so this would also be negative. Okay, so now in this we can see that y is negative. So as we discussed in the previous video for crystallographic directions, if we had a negative sign, we used to change the origin. In this we'll be shifting the origin to in the y direction. So this would be now the origin would be 0 for y, and this would be 1 for y. So we are going negative 1 in the y direction, so to the point. Then we are going half in the z direction. So this is z direction, positive z direction. This would be half, and this would be half in the x direction, which is the positive. So this would be our plane for 2 negative 1. Again, if we have a measure index given us as 2 1 and negative 2, now So what we'll do is first we'll just take the inverse of this, that is 1 by 2, 1 again, and 1 by 2 the negative piece. This will be the again the intercepts of this. So in this, the origin will be shifted to that direction, that is 0 for the z and 1 for the z axis. So we have to move 1 by 2 in the z direction. So this would be 1 by 2 in the z direction, 1 by 2 in the x direction. From here we'll be moving 1 by 2 in the x direction and 1 in the y direction. So 1 in the y direction. Basically this would be our plane. Okay, so I hope that this was enough practice for major indices for crystallographic planes. So now let's discuss some properties. In a cubic plane and their negatives are equivalent, you see that in the same family, the opposite planes, the negative planes are equivalent but in the opposite direction. And in the cubic system, a plane and a direction with the same index are perpendicular. As we discussed in this question, that plane having, this is the plane as you can see in the gray, and this has the direction 1 0 0. So the plane 1 0 0 and the direction 1 0 0. You can see that the direction is perpendicular to this plane. Same for this one, that is 1 0 0 plane. This one, and the direction is 0 1 0 for 0 1 0 plane, and this is again perpendicular to this. Same with 0 0 1. In this you can see that the plane 0 0 1 has the same direction 0 0 1, but it is perpendicular to the plane. Okay. So how do we measure these major indices? Basically, this is an XRD scheme. It's an XRD technique in which we use X-ray diffraction to identify the planes, and with that we can calculate the compound which is formed. We are doing an experiment or any other thing. If we want to identify compounds in a product or in a material, so we use this technique which identifies the major indices, and then we compare it with the standard, and we get an answer that what kind of a bond or what kind of compound exists in our sample. So it measures the average spacing between layers of or row of the atom, again, which I told determines the orientation of a single crystal or grain. It determines the orientation, that again the direction and the planes. It finds the crystal structure of an unknown material. Again, the unknown if the material is unknown, we don't know that what compounds do we have in our sample. So we'll be getting some planes and some direction, and we'll be comparing it with the standard. So we'll identify that certain material or a certain compound we have in our sample, and it measures the size, shape, and internal stress of small crystalline. So this is basically a graph obtained by the XRD of any sample. This is XRD pattern for NaCl powder. So we know that this 220 and 200 major index has been identified in the graph. This is the intensity and the diffraction angle. And these are the major indices. So we know that 222 plane exists in NaCl. So our majority of the compound is sodium chloride. So that was all for this video. Thank you.